Hello, hello. This is part 2 of section 1.8 in linear algebra, defining a transformation to be linear if for all vectors u and v in the domain of the t, that is a function t, and all scalars, c is a scalar, we have the transformation of the sum of the vectors in the domain to be the sum of the transformations, that's rule 1, and also the transformation of a scalar multiple of a vector in the domain is equal to that scalar times the transformation of the original vector. Part 1, Part 2, memorize these two parts for your Chapter 1 exam. So every matrix transformation is a linear transformation. Every matrix transformation is a linear transformation. So the ones that we've been doing, right? Let's look at t is a linear transformation. Then two things are going to be true. T of 0 vector is the 0 vector, and t of the combination cu plus dv is the scalar times the transformation plus the other. When you do this t of 0 is 0, please, 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 that's only to prove, if you're trying to prove something's not a linear transformation, you can use that and say, hey, it's not 0. However, if you're proving something is a linear transformation, you've got to go back to those two rules in the previous slide. Let's look at an example. Suppose you have a transformation t given below, and so t of the input vector, the three-dimensional input vector, gives you that result, absolute value of the first and third elements, followed by 2 plus 5 times the second element of the domain. So we can really easily see that t of 0 is not equal to 0. Therefore, this is not a linear transformation. Just to review the ideas of domain and codomain, though, the domain has 3 elements in it, x1, x2, and x3. So the domain is three-dimensional space, and then the codomain is two-dimensional space because B is a 2 by 1 vector. Another example, using the same a different t of x1, x2, x3. This time I'm just taking out the 2 plus thing here so that t of 0 is 0. So now we've got to go to the definition to prove that it is or isn't a linear transformation. And the easiest part of that definition is rule 2, where you have the scalar multiple, -1, times the input vector, x1, x2, x3 here. I do perform the transform on that. So first -1 times all of those things, and then perform the transformation on that. The absolute value of the negatives is just the, what is that? That's the same as, you could factor out the -1, absolute value of -1 goes away. It's just absolute value of x1 and x3. However, this does change to a -5x2. So that's t of -1 times the input. Is that the same as -1 times the transformation of the input? Okay, this is rule 2. Rule 2 right here. That's what we're showing, but with c -1. All right, so -1 times this thing is the opposite of the absolute value. So the negative of the absolute value is not the same as the absolute value. They're not the same. Therefore, rule 2 is violated. It's not a linear transformation. For this matrix A below and the vector B, determine if B is in the range of the linear transformation. So you can take an augmented matrix, and we're going to see, does AX equal B? Does it have a solution? If so, B is actually in the range. We know B is in the codomain of R4. What we don't know is it an actual solution? So I do the RF, do the reduced row echelon form, and we get down here, does 0 ever equal 1 1/4? No. So there's no solution. That means there's no b. The b is in the codomain, but it is not in the range. So no, no is the answer because b is in the codomain of R4, but not in the range. Is the transformation onto? Well, no, to be onto every b must be in the range. Another example, we're going to go from R3 to R3, and T is the transformation reflecting each vector, each input vector in R3 through the plane. X3 is 0, and so you're reflecting it that X1 and X2 stay the same, but X3 becomes negative. So is X3 is 0, is that really a plane or is that a line? If Z is always 0, no, that would be a plane. Think about it. X, Y, Z. Z is 0, so X and Y would stay the same, and then Z would be flipped. Okay, so show T is a linear transformation. In order to show it is a linear transformation, 2 rules apply. So first rule, show the transformation of the sum is the sum of the transformations. And then secondly, we'll show in a second over here, rule 2, that the transformation of the scalar times the vector is the scalar times the transformation of the vector. So first rule, what is T of U plus V? We'll do T of U plus V. So do U plus V. So what's U plus V? U is U1, U2, U3. V is V1, V2, V3. So add U and V, you get U1 plus V1, and then U2 plus V2, and then U3 plus V3, and perform the transformation on it. So the first 2 elements, X1 and X2, stay the same, but the third one is reflected through that plane. Z is 0, or X3 is 0, and you get the negatives. Now do T of U separately from T of V. So here's T of U, here's T of V, and now add them, and voila, we get the same thing. So rule 1 is done. Now let's look at rule 2, scalar multiple rule. So here's my input, here's my output. What's T of CU? So here's CU. We should have said U1, U2, U3, but okay. Pretend like that says U1, U2, U3. And then CTU, again, pretend like this says U1, U2, negative U3. But anyway, you would get the exact same thing. So both parts of the definition hold true. T is a linear transformation. Here's your homework. Good luck. Take care. Bye.